this video, we're heading back into the world of limits. But this time, things are heating up. We're tackling the spicy ones, the kind we skipped back in Chapter 1. Why now? Because you've got a brand new superpower, differentiation. And here's the best part. Once you know how to differentiate, these tougher limits aren't nearly as scary. It's basically like unlocking cheat mode for calculus. Before we dive into this video, hit pause and go back to the one where we worked through algebraic limits and our original game plan for solving them. In that video, we said that when a limit gives us outcome number 2, where we end up with a fraction that has 0 over 0, we call it an indeterminate form. I also mentioned that we'd come back later to explore this form in more detail. Well, later is now. In this lesson, we're upgrading our game plan so we can take on these tougher limits head-on. I recommend rewatching the video on algebraic calculation of limits before jumping in here, just so you don't get lost along the way. In short, we saw that sometimes we're given limits to solve algebraically, meaning we don't have the function's graph to visually check whether the limit exists or not. For those situations, we had a game plan. We started by substituting the limit approach value directly into the limit. This would give us one of 3 possible outcomes. Outcome 1. Substitution works perfectly, no issues, and we can punch it straight into the calculator to get our answer. Outcome 2. Substitution gives us a 0 over 0 situation. On the calculator, this shows up as a math error. This is what we call an indeterminate form, and here our approach was to factor and cancel before finding the answer. Outcome 3. Substitution gives us a number, not 0, divided by 0. That's also a math error, but for a different reason, division by 0. In this case, our next step was to do a sign analysis to determine the limit. In this video, we're going to take a deeper dive into outcome 2, the indeterminate form. All right, let's kick things off with an example of an indeterminate form. We know an indeterminate form happens when we substitute the limit approach value into the function and end up with a 0 over 0 fraction. Our game plan in this situation is to factorize and cancel out the problem term so we can actually find the limit. When we do that here, we get the following answer. But what happens if we get an indeterminate form and factoring is either way too messy or just not even possible? Like in the next example. If we plug in the limit approach, we see we get a 0 over 0 situation. According to our original game plan, this means we should factor. But in this case, it's clear there's no way to factor it so that the denominator cancels and we can solve the limit. So, what now? Well, this is where you meet a brand new math power-up, something called L'Hopital's rule. Guillaume de L'Hopital was a French nobleman, mathematician, and, fun fact, totally into calculus before it was even cool. He didn't actually invent the rule that now carries his name. Most of the credit goes to Johann Bernoulli, one of the calculus legends of the time. But he's the one who made it popular and turned it into a go-to tool for students like you. So, how does this rule actually work? They noticed something interesting happens when you differentiate a limit that's in indeterminate form. Let's see it in action. We'll take the same example as before, but this time we'll use L'Hopital's method. Here's the deal. When a limit is in indeterminate form, you can apply L'Hopital's rule by differentiating the numerator and denominator separately, just like this. This is exactly why we're only covering it now. You first need to know how to differentiate. Once we differentiate both parts and plug the limit approach back in, we get our answer. And look at that. It's exactly the same answer we got earlier when we factored and canceled. That means we can now use this method to solve indeterminate form limits that can't be factored. Magic. Now we can go back to that example we got stuck on earlier because factoring was not possible, and use L'Hopital's rule to finally crack it. We start by plugging in the limit approach, and we can see it gives us 0 over 0, which is an indeterminate form. Normally, our game plan would be to try factoring, but here it is clearly not going to work. So, we bring in our new math tool, L'Hopital's rule. Remember, you can only use L'Hopital's rule for limits that are in indeterminate form. That is the only time it works. Here is how. We differentiate the top and bottom of the fraction separately. This is where your trig differentiation skills matter. If you are a bit rusty, go back to the video where we covered them. For the numerator, we can see it as a composite function because of the power of 3, so we use the chain rule to handle that and get our answer. For the denominator, it is a nice simple function, so we can just differentiate it directly using the trig table. Once we have differentiated, we simplify. Here, the cosines on top and bottom cancel out nicely. Now we try plugging in the limit approach again, and voila! We have got the answer to the limit using L'Hopital's rule. In this example, we're looking at another limit problem that starts off in an indeterminate form, but this time, something a bit unusual is going to happen that teaches us an important trick about L'Hopital's rule. Let's dive in. As always, we start by substituting the value that the limit approaches. Right away, we see we're stuck with a 0 over 0 fraction, which means it's an indeterminate form. Perfect! We can use L'Hopital's rule. So we apply L'Hopital by differentiating the top and bottom separately, and we get a new expression. We plug in the limit value again, and boom, still stuck in indeterminate form. Another 0 over 0. Now what? Here's the key thing you need to remember. You can use L'Hopital's rule more than once in a row to get yourself unstuck from an indeterminate form. So we apply L'Hopital again, differentiate top and bottom separately, and try substituting the limit once more. This time, it works, and we get a final answer for the limit. If we had gotten 0 over 0 again, we could have just repeated the process. You keep applying L'Hopital until you're no longer in an indeterminate form and can successfully substitute to get the answer. Bottom line, don't freak out if you use L'Hopital's rule once and still end up with an indeterminate form. Just keep applying it, step by step, until you break free from the 0 over 0 trap and can finally evaluate the limit. Now, for the last part of this video, we're going to see how we can use L'Hopital's rule when working with limits as x approaches infinity. Let's look at an example. Important, if you haven't watched the video where we did limits to infinity using the chocolate sharing fractions analogy, go watch that first. Otherwise, this will make absolutely no sense. All right, let's dive in. In this example, we're given a limit as x goes to infinity. The first thing we always do in limits to infinity is figure out whether we're dealing with a polynomial function or a rational function, because we handle them differently. Here, it's a rational function because there's an x in the denominator. Again, if that still sounds like Greek to you, pause and watch the limits to infinity video before continuing. For rational functions, we divide everything by the highest power of x in the denominator. In this case, the highest power is x to the power of 1, so we divide everything by x to the power of 1. This gives us our chocolate sharing fractions. A chocolate sharing fraction is when you take any finite number and divide it by infinity, at which point we can replace it with 0. But here's where things get interesting. When we try substituting infinity, we end up with Euler's constant raised to the power of infinity, over infinity. Let's think about that logically. Euler's constant is just a number, so raising any number to the power of infinity will still give us infinity, because a huge exponent makes a huge result. So really what we have is infinity over infinity. Warning, infinity over infinity is not 1. Infinity is not a number, it's a concept, so it doesn't behave like regular numbers, where 8 over 8 is 1. In fact, infinity over infinity is just like 0 over 0, in that it's an indeterminate form. Your calculator wouldn't know what to do with it. And this is exactly when we can use L'Hopital's rule. We differentiate the numerator and denominator separately, then try substituting again. This time, we get a chocolate sharing fraction, a normal number divided by infinity, which equals 0. Boom, there's our limit. Summary. L'Hopital's rule can only be used when you have a limit that's an indeterminate form, most commonly 0 over 0. But remember, infinity over infinity also counts as 1. So whenever a limit going to infinity gives you infinity over infinity, you can use L'Hopital's rule to break it down and solve it successfully. To wrap up, and with this, we're closing the video. Enough maths for one day. When we're working out limits algebraically and we get an outcome where substituting the limit value gives us 0 over 0, or importantly, don't forget infinity over infinity, then we're dealing with an indeterminate form limit. As we explained in our first video, our usual move here is to try and factor so that we can cancel the denominator. But now we have a new maths tool that helps us with the cases where factoring isn't an option, and that's L'Hopital's rule. The key thing to remember is, L'Hopital's rule only works if the limit is in indeterminate form. To apply it, we differentiate the top and bottom of the fraction separately, and then try substituting the limit again. This neatly clears up the 0 over 0 situation. And if it doesn't, remember, you can apply L'Hopital's rule consecutively until you break free from the 0 over 0 trap. Winging calculus is like winging a parachute jump, fun until the ground shows up. Ditch the 30 open YouTube tabs at 2 a.m. trying to integrate and grab my ebook course, step-by-step fixes and shortcuts. Cheaper than your monthly coffee bill and way easier than explaining a flatlining GPA. Course link in the description. If this helped, smash like and subscribe. See you next time. Cheers!